So in this video, we're going to look at some applications of triple integrals. So imagine that we've got a solid region, solid three-dimensional region in space. Let's call that T. And we can use triple integrals to calculate a few useful things. So first of all, we could say mass is the triple integral over our solid T of delta dV. So you may remember from one of our previous videos that delta here just represents the density of our solid at all these different points in space. We could talk about the centroid or center of mass. So in symbols, we'll write x bar, y bar, z bar for the coordinates of our centroid. And we could actually calculate these coordinates using a triple integral. So we go 1 over the mass times the triple integral over our solid T of x delta dV. So let's talk about units here and just make sure that units-wise everything makes sense so far. So delta would be in units like kilograms per meter cubed. And then our dV would be something like, typically it would be dz, dy, dx, but it could be one of the other orders of integration as well. So if each of x, y, and z were measured in meters, then this dV would be meters cubed. So you'd have kilograms per meter cubed times meters cubed gives you kilograms for mass. So that makes sense unit-wise. Let's talk about the units for the centroid. So as we just said, delta dV will be measured in kilograms. If we multiply that by x, the units are now kilograms times meters. And if we divide by mass, then we're dividing through by kilograms. So we get back to meters. So therefore, this expression here is giving us a value in meters, and specifically what it's giving us is the x-coordinate of the center of mass. So if you wanted your y bar or z bar coordinate, it would be exactly the same formula, but just with a different variable in the integrand. So triple integral of y delta dV divided by the mass if we wanted y bar. If we wanted z bar, 1 over the mass, triple integral over our solid region, z delta dV. And then last thing we could talk about is moments of inertia about our various axes. So if we want the moment of inertia about the x-axis, notationally we're going to write I sub x. This is going to be the triple integral over our solid region T of y squared plus z squared delta dV. I'm just going to draw a picture here in 3D of what this represents. So let's say you've got a solid region, three-dimensional region here at T, and we're talking about rotation about our x-axis. So you're going to imagine this region here rotating about your x-axis, possibly coming over here. So in this context, the x-coordinate of these different points will not be changing, but as the rotation happens, the y and z coordinates will be changing. Now, one big determining feature of the moment of inertia is the distance of every point in this region from the axis about which you're rotating. So if you imagine we're in 3D space here, we're talking about the distance between this point here and let's say the x-axis. Let's draw a picture, that distance. So that distance would depend on y and z, but would not depend on x. And in fact, it's the distance squared that we want to calculate. So it turns out that the distance squared is y squared plus z squared. So your moment of inertia is the tendency to resist angular acceleration about whatever axis you're looking at. So the bigger this number, the less likely your solid region is to rotate about that axis. So similarly, we could write down the moments of inertia about the y-axis or the z-axis. So for I sub y, triple integral over our solid region T, it's going to be x squared plus z squared delta dV. So when you look at this sum of squares, it's always involving the other two variables. If you're doing rotation about the y-axis, distance squared to the y-axis is determined by x squared plus z squared. And then similarly, I sub z, triple integral over t, x squared plus y squared, delta dv. So let's talk quickly about units here for moments of inertia. We know from our previous discussion that delta dv would give us units of mass. So that's going to be kilograms. And if we then multiply by something like y squared plus z squared, then we're multiplying meters squared on there. Then the integrals themselves don't contribute to the units because you're just summing up these types of quantities. So units for moments of inertia, kilograms times meters squared. Same units as you have if you do two-dimensional moments of inertia. In this problem, we're going to find I sub y, so that's the moment of inertia with respect to the y-axis for the solid described below, and we're given our density function. So density at every point throughout the solid is equal to y. All right, so here's our solid bounded by 5 different planes. So let's see if we can draw them. Z equal 4 minus x. Going to have x and z intercepts of 4. So I'm just going to draw that as a line for now, but it's really a plane. So there's our z equal 4 minus x. We've got x equals 0 and z equals 0. Okay, so let's draw x equals 0 like that, z equals 0 like that. And then we've got a few different y values also forming the boundary. So y equals 0 is sitting right in the xz plane, and then we can step over 4 units for y, let's say there, and this is forming another cutoff. So let's visualize that we've got a copy of this triangle here. We've got a copy of that at every y value. We're interested in doing this just between y equals 0 and y equal 4. So we're essentially getting this sort of a shape here, and I think I'll label the different surfaces on this diagram. So at the bottom, we've got z equals 0. And at the back, we've got x equals 0. So that's like saying stop before you get into any negative x values. On the sides here, we've got our y values. So y equals 0 right on the xz plane, and then y equal 4 is forming the right cutoff of this. And then we've also got this slanted surface, which I'll draw in black. Okay, so that right there is coming from z equal 4 minus x. So we've got this 5-sided solid there. We're going to need to set up a triple integral to describe this region that's being enclosed. So let's slice in the z direction. That's usually the go-to. Okay, so just imagine drawing a slice going vertically like that in the z direction through this region. Z values would be going from z equals 0 at the bottom where they're hitting the xy plane, and they would be going up to this slanted plane here, just hitting these black lines that you can see slanting to form the front of this solid. So z could be getting as big as 4 minus x. Okay, and then once we figured out our limits of integration for z, we need to project onto the xy plane. So if you do that geometrically, just imagine standing up here at a high z value, looking down on your solid and figuring out what are all the points that would be enclosed in that solid. So you'd actually be getting a rectangle, in fact a square, in the xy plane. So let's just label our axes here. So we'd be going up to y equal 4, and we'd be going over as far as x equal 4. Okay, so there's our nice square. It's going to be shaded in. So that's our projection on the xy plane. If you want to think about that projection from an algebra point of view, as opposed to a geometry point of view, then you would say, okay, well, let's list all the surfaces that are forming the boundaries here, but we're going to try to eliminate z from them. So we would take, let's do this over on the side. So we would take z equal 4 minus x, and we would plug maybe z equals 0 into that. So that's just going to eliminate z. That's going to give us 0 equals 4 minus x as one of our equations. So that takes care of these two equations. And then the other equations just involve x and y. Okay, so there we've taken our 5 equations, we've eliminated z from them, and so that now gives us a set of 4 equations. The 4 equations now say x equals 4, x equals 0, y equals 0, y equals 4. So sure enough, we're getting our x equals 0, x equals 4, y equals 0, y equals 4, and then we understand, okay, that's a square. So this is the algebra version of projecting on the xy plane, and this is the geometry version of projecting on the xy plane. So you can do one or the other or both just to reinforce that you're doing this correctly. Okay, so however you decide to do your projection, we then need to set up our limits of integration for x and y. Let's do vertical slices here. So we would say y goes from 0 to 4 and x goes from 0 to 4. And what that does for us is allows us to now set up our triple integral. So I'm going to highlight our 3 different limits of integration. We know what's going on with z, y, and x, and now we can jump into setting up our integral. So remember, what we wanted in this problem was moment of inertia with respect to the y-axis. So in general, you'd say that's the triple integral over our solid of x squared plus z squared times delta times dv. And we were told in this problem that delta is y. So in this context, you would just be given the formula for delta as part of the problem. And then for your dv, you can choose whatever order of integration you think is going to work well. I would say dz, dy, dx is what you do most of the time, at least as your first attempt. And only if something goes wrong with that do you try a different order of integration. Okay, so let's make this specific. We're going to fill in our limits of integration here. Our integrand is going to look like x squared plus z squared times y, and then we'll have our dz, dy, dx. Since we're going to be integrating with respect to z first, I would suggest it might be better to actually multiply out that integrand. Well, you could go either way here, but I'm just going to choose to expand it out just so we can take the integration more step by step. Okay, so integrand x squared y plus z squared y, and then we'll just get our limits of integration on there. So we said z was going from 0 to 4 minus x, and we said that both y and x were going from 0 to 4. So if the problem were just to set up a triple integral for I sub y, we would be done. But we're actually going to practice the concept of triple integration here to finish off the problem. So we're going to start with the innermost integral. We are going to integrate with respect to z. So we keep our outside 2 integrals on there. Keep our last 2 differentials at the back, and let's integrate with respect to z. So x and y are both constant with respect to z. We'd get x squared yz plus z cubed y over 3 when we integrate with respect to z. And then we have to evaluate at z equals 4 minus x and z equals 0. So we'll do our evaluation in the next step. Okay, so x squared y times 4 minus x plus 4 minus x cubed times y all over 3. And then we would need to subtract off the values at 0, but both those terms are going to be 0 at z equals 0, so we don't need to worry about that. And we've now produced a nice double integral. All right, so let's next integrate with respect to y. We'll keep our outside integral and outside differential on there. Integrating with respect to y, all the x terms are constants. So you get something like x squared times 4 minus x. Just think of that as your coefficient. Integral of y is y squared over 2. And then for this second term here, same kind of deal. 4 minus x cubed is a constant. Integrating y, you get y squared over 2. So our denominator is now 6. Okay, and then that's got to get evaluated at 4 and then at 0. Probably a good idea to write y equal 4 and y equal 0 there so that we know what we're subbing in. So a couple more steps to go. We still got our outside integral and our outside differential on there, and let's start subbing in. So when y equal 4, y squared over 2 is going to be 8. So we're going to have 8x squared times 4 minus x. Plus, for the second term, y squared is now going to be 16. So I'll say 16 over 6 times 4 minus x all cubed. And then subtracting off the values at y equals 0, both those terms are going to be 0. So that's nice. So we just get those two terms there. And then we've got an integration with respect to x left. So before we go into the integration, let's just clean up these terms, get them ready for integration. I'm going to expand this first part out and call that 32x squared minus 8x cubed. And then for the second term, we can leave that as is, but I might just clean up that coefficient. Let's make it 8 over 3 instead of 16 over 6, just to keep the numbers as nice as possible. Okay, so let's try our integration. Integrating with respect to x, 32x cubed over 3 minus, this is going to be 2x to the 4th. And then we're going to have, well, let's think about this, 4 minus x to the 4th over 4. If you actually went through the details of the substitution, you'd get a minus sign coming up. That is because if you let u equal 4 minus x, your du would actually be minus dx. So if you wanted to do a substitution on the side, you could, but I would just tend to do this a little quicker and say that's minus 4 minus x to the 4th over 4, and that's still times the 8/3 that we had in front there. So I'll say it's 8/3 times minus 1 times 4 minus x to the 4th over 4. That's just my fast way of doing substitution. And then we still need to evaluate this at 4 and then at 0. So before plugging in, I just want to clean up these coefficients on that last term a little bit. Let's call the coefficient minus 2/3 just to make it a bit cleaner, and then we can start subbing everything in. Okay, so evaluating at x equal 4, we get 32 over 3 times 4 cubed minus 2 times 4 to the 4th. And then this last term, when we sub in x equal 4, is going to be 0, so that's nice. And then we need to subtract off the values at x equals 0. Okay, well at x equals 0, the first two terms are 0, but the third term is not. We're going to have minus 2/3 and then 4 to the 4th when we evaluate at 0. So grabbing a calculator, you can confirm that comes out to 1024 over 3. So that gives our moment of inertia for that solid region with respect to the y-axis. We not only got a little bit of practice with moment of inertia, but we also got some practice with setting up another triple integral for a solid region in 3D. Thanks for watching.